Welcome to the fascinating world of nanoscale physics, where the rules of friction change dramatically. At the nanoscale, 1/1000th of a meter, the physical world operates under dramatically different rules than our everyday experience. Let's start by understanding just how small the nanoscale really is. 1 nanometer equals 10 to the power of -9 meters, or 1/1000th of a meter. To put this in perspective, a nanometer is to a meter what a marble is to the entire Earth. A single human hair is about 80,000 nanometers wide. A DNA double helix is just 2 nanometers wide. Before diving into the nanoworld, let's review how friction works at the scale we're familiar with. At our scale, friction opposes motion. Push a block across a surface, and friction pushes back. The classical friction equation states that friction force equals the coefficient of friction times the normal force. Traditional friction depends heavily on surface roughness and the real area of contact between surfaces. But here's the fascinating question. What happens to friction as we shrink objects down to the nanoscale? At the nanoscale, the fundamental physics of friction transforms dramatically. At nanoscale, individual atomic interactions dominate. Each atom can be thought of as a tiny sphere interacting with neighboring atoms. Surface area scales with length squared, but volume scales with length cubed. So the surface-to-volume ratio increases dramatically as objects get smaller, going as 1 over length. This means, as we shrink down, surface effects completely dominate over bulk properties. At nanoscale, a new player enters the game, the van der Waals force. Van der Waals forces are weak attractive forces between atoms caused by temporary fluctuations in electron clouds. The van der Waals force decreases with distance cubed, where A is the Hamaker constant and D is the separation distance. Individual van der Waals interactions are incredibly weak, about 1/100th the strength of a hydrogen bond. However, at nanoscale, millions or billions of atoms can interact simultaneously, making these forces collectively very significant. To understand nanoscale interactions better, we use the Lennard-Jones potential. The Lennard-Jones potential describes how the potential energy between two atoms varies with their separation distance r. This graph shows the Lennard-Jones potential. Notice the steep repulsive wall at close distances and the attractive well at moderate distances. The r to the 12th power term creates strong repulsion when atoms are pushed too close together. The r to the 6th power term creates weak attraction at moderate separation distances. Now let's calculate actual friction values at nanoscale. Consider a contact area of 1 nanometer squared between two surfaces. In 1 square nanometer, we have roughly 4 atoms at the interface. Each van der Waals bond has energy around 0.1 electron volts, or about 1.6 times 10 to the -20 joules. The total binding energy is 4 times 1.6 times 10 to the -20 equals 6.4 times 10 to the -20 joules. The friction force equals energy divided by distance, giving approximately 2 times 10 to the -10 newtons. This is an incredibly tiny force, 0.2 nanonewtons. Let's compare friction at different scales to see the dramatic difference. Compare a 1 centimeter cube at macroscale to a 1 nanometer structure at nanoscale. At macroscale, with coefficient of friction 0.5, friction might be 0.05 newtons, equivalent to 5 grams of force. At nanoscale, friction is 2 times 10 to the -10 newtons, which is essentially 0 compared to macroscale. The ratio of macro to nano friction is about 250 million to 1. This raises an intriguing question. Does this mean nanomachines can move forever without friction? Let's examine the reality of friction at nanoscale through the science of nanotribology. Nanotribology is the study of friction, wear, and lubrication at atomic and molecular scales. When one atomic layer slides over another, atoms must overcome energy barriers as they move from one equilibrium position to the next. The key insight is that friction is not actually zero at nanoscale, just dramatically reduced compared to macroscale. Nanoscale motion exhibits stick-slip behavior, where atoms stick in energy wells, then slip to the next position. Energy barriers for atomic motion are typically 0.01 to 0.1 electron volts per atom. Now we can answer our central question: can nanomachines move forever? The answer is no. Nanomachines cannot move forever, but they can operate for remarkably long periods. Imagine a nanoscale motor with rotating components experiencing ultra-low friction. Energy loss per rotation might be around 10 to the negative 20 joules. If we input 10 to the negative 18 joules per cycle, we achieve efficiency around 99%, far better than any macro machine. With minimal continuous energy input, such a nanomachine could operate for millions or billions of cycles. Nature has already solved the problem of building efficient nanomachines. ATP synthase is a molecular motor in our cells that produces ATP, the energy currency of life. This incredible nanomachine exists in every cell of your body right now. It rotates at 100 to 400 revolutions per second. Its efficiency exceeds 90%, far better than any human-made motor. The entire structure is only about 10 nanometers in diameter. Each rotation produces 3 ATP molecules, the energy packets that power cellular processes. This design has been operating successfully in living cells for billions of years of evolution. Building artificial nanomachines presents unique challenges, despite low friction. 3 major challenges face artificial nanomachine designers: adhesion, wear, and assembly. First challenge. At nanoscale, surfaces tend to stick together strongly due to van der Waals adhesion. Adhesion forces can be much greater than friction forces, causing parts to stick. Second challenge. Even with low friction, atomic level wear gradually damages components. Third challenge. Manufacturing nanomachines with atomic precision remains extremely difficult. The Strybeck curve helps us understand friction behavior across different velocity regimes. The Strybeck curve shows how friction varies with sliding velocity through 3 regimes: boundary, mixed, and fluid. At nanoscale, we typically operate in the boundary regime, where surfaces are in direct atomic contact. Friction coefficients at nanoscale range from 0.001 to 0.1 compared to 0.5 or higher at macroscale. Temperature introduces another important effect at nanoscale: phonon drag. Atoms in a solid vibrate thermally, creating waves of atomic motion called phonons. Thermal energy at room temperature is kBT, approximately 4 times 10 to the negative 21 joules per atom. These phonons scatter electrons and create resistance to motion, contributing to friction. Phonon drag increases with temperature squared at low temperatures. This means, at very low temperatures near absolute zero, friction drops even further than at room temperature. At the smallest scales, quantum mechanics becomes important. The de Broglie wavelength lambda equals Planck's constant divided by momentum. For a mass of 10 to the negative 26 kilograms moving at 1 meter per second, the wavelength is about 10 nanometers. At sub-nanometer scales, quantum tunneling allows particles to pass through energy barriers. Particles can quantum tunnel through barriers that would be impassable in classical physics. Quantum tunneling can further reduce effective friction at the very smallest atomic scales. Under special conditions, we can achieve superlubricity, an extreme form of low friction. Superlubricity is defined as a friction coefficient, less than 0.001. Superlubricity occurs when 2 crystal surfaces are misaligned, preventing atoms from interlocking. This has been achieved experimentally with graphite sliding on graphite at specific misalignment angles. In superlubricity conditions, friction can be 10,000 times lower than normal nanoscale friction. However, achieving superlubricity requires atomically flat surfaces in very specific conditions. Even with ultra-low friction, energy dissipation still occurs through several mechanisms. Energy dissipates from nanomachines through multiple channels, primarily converting to heat. First, phonon emission occurs as moving atoms create vibrations that spread as heat. Second, electron-phonon coupling creates electrical resistance in conductive materials. Third, adhesion hysteresis from repeatedly making and breaking atomic bonds dissipates energy. Power dissipated equals force times velocity. For example, 10 to the negative 10 newtons times 1 meter per second equals 10 to the negative 10 watts. This is an incredibly tiny power, just 0.1 nanowatts. Understanding nanoscale friction enables revolutionary applications. Applications include nano-electromechanical systems, targeted drug delivery, ultra-sensitive sensors, and quantum computing devices. Nano-electromechanical systems use movable parts operating with minimal energy consumption. Researchers are developing synthetic molecular motors inspired by biological examples like ATP synthase. Future data storage might use atoms positioned on surfaces, with read-write mechanisms exploiting ultra-low friction. Let's calculate the actual lifetime of a nanomachine operating continuously. Assume wear removes 1 atom per 10 billion operations. A small nanomachine might contain 1 million atoms total. Perhaps 10,000 of these are critical atoms whose loss would cause failure. The lifetime is 10,000 times 10 billion equals 100 trillion operations. Operating at 1 megahertz, that's roughly 3 years of continuous operation. What does the future hold for frictionless nanomachines? The future of nanotechnology holds much promise for the development of advanced nanomachines that can exploit ultra-low friction for new applications and innovations.